AHA Sciencer. Welcome to AHA channel. In this channel you will learn about science knowledge. In this section you will learn about Newton's law. Newton's laws of motion are three basic laws of classical mechanics that describe the relationship between the motion of an object and the forces acting on it. These laws can be paraphrased as follows. A body remains at rest, or in motion at a constant speed in a straight line, unless acted upon by a force. When a body is acted upon by a force, the time rate of change of its momentum equals the force. If two bodies exert forces on each other, these forces have the same magnitude but opposite directions. The three laws of motion were first stated by Isaac Newton in his Philosophiae Naturalis Principia Mathematica, Mathematical Principles of Natural Philosophy, originally published in 1687. Newton used them to investigate and explain the motion of many physical objects and systems, which laid the foundation for classical mechanics. In the time since Newton, the conceptual content of classical physics has been reformulated in alternative ways, involving different mathematical approaches that have yielded insights which were obscured in the original, Newtonian formulation. Limitations to Newton's laws have also been discovered. New theories are necessary when objects move at very high speeds, special relativity, or very massive, general relativity, or are very small, quantum mechanics. Newton's first law expresses the principle of inertia. The natural behavior of a body is to move in a straight line at constant speed. In the absence of outside influences, a body's motion preserves the status quo. The modern understanding of Newton's first law is that no inertial observer is privileged over any other. The concept of an inertial observer makes quantitative the everyday idea of feeling no effects of motion. For example, a person standing on the ground watching a train go past is an inertial observer. If the observer on the ground sees the train moving smoothly in a straight line at a constant speed, then a passenger sitting on the train will also be an inertial observer. The train passenger feels no motion. The principle expressed by Newton's first law is that there is no way to say which inertial observer is really moving and which is really standing still. One observer's state of rest is another observer's state of uniform motion in a straight line, and no experiment can deem either point of view to be correct or incorrect. There is no absolute standard of rest. Newton's first law reads, "Every body continues in its state of rest, or of uniform motion in a straight line, unless it is compelled to change that state by forces impressed upon it." Newton's second law. The change of motion of an object is proportional to the force impressed, and is made in the direction of the straight line in which the force is impressed. By motion, Newton meant the quantity now called momentum, which depends upon the amount of matter contained in a body, the speed at which that body is moving, and the direction in which it is moving. Newton's third law. To every action, there is always opposed an equal reaction, or, the mutual actions of two bodies upon each other are always equal, and directed to contrary parts. Overly brief paraphrases of the third law, like, action equals reaction, might have caused confusion among generations of students, that action and reaction apply to different bodies. For example, consider a book at rest on a table. The Earth's gravity pulls down upon the book. The reaction to that action is not the support force from the table holding up the book, but the gravitational pull of the book acting on the Earth. Newton's third law relates to a more fundamental principle, the conservation of momentum. The latter remains true even in cases where Newton's statement does not. For instance, when force fields as well as material bodies carry momentum, and when momentum is defined properly, in quantum mechanics as well. Newton's law of universal gravitation states that any body attracts any other body along the straight line connecting them. The size of the attracting force is proportional to the product of their masses, and inversely proportional to the square of the distance between them. Finding the shape of the orbits that an inverse square force law will produce is known as the Kepler problem. The Kepler problem can be solved in multiple ways, including by demonstrating that the Laplace-Runge lens vector is constant, or by applying a duality transformation to a two-dimensional harmonic oscillator. If a third mass is added, the Kepler problem becomes the three-body problem. which in general has no exact solution in closed form. That is, there is no way to start from the differential equations implied by Newton's laws and, after a finite sequence of standard mathematical operations, obtain equations that express the three bodies' motions over time. Thanks for watching.